No one wants it. That's all. Okay. So, before we get started today, I've been slowly making my way through your electrochemical driving force equilibrium potential assignment that was due on Tuesday, and they're looking pretty good, but I wanted to go through one of the ones that seems to be coming a couple people up, because it's going to come into play as we talk about our synapses and our neuronal connections in a little while. The one that I've seen has been giving people a little bit of trouble is our calcium. Okay, so what we're looking at, we're all in this assignment, you're all looking for the chemical driving force, the CDF, the electrical driving force, the EDF, and then adding those two together for our electrochemical driving force. And I think the reason that some of us had a little trouble with this one has to do with the units on the concentrations. So you do have to be a little careful here. Our ICF concentration was actually given in nanomoles instead of millimoles because it is so small. Okay, so in order to do this example, we need to do the conversion here. Okay. So reminder, when we're converting, we can use conversion tables like this. So most of these concentrations were in millimoles with an M, but that ICF for calcium was given in nanomoles, an N. All right, so we are much, much smaller if we're looking at a nanomole. All right, so our conversion then, take those 70 nanomoles, do just like you do in your lab courses, right? We can cancel out those nanomoles and turn it into millimoles by dividing by a million, okay? Which would have given us 0.00007 millimoles for that concentration. So if you had some trouble figuring out why that electrochemical driving force was in the direction that the calculator is showing you, that is what accounts for it. Okay, so our CDF, our chemical driving force here, would have been from the higher millimoles to the lower, right, 0.0007 millimoles given in nanomoles because it's that small. Okay, so that would have been the CDF. Okay. Our EDF, we have our positive calcium ion, okay? And in fact, it has a different valence than our other positive ions. So this does make a difference, not for the direction, but for the strength of that force. The direction, positive, that positive is going towards this negative membrane potential. So our EDF in that same direction, okay, as our CDF. Okay. We get a huge electrochemical driving force into the cell as a result. And calcium also plays a role when we get to the heart, thinking about how that functions. So that's worth knowing for that part as well. Okay. So we have a very big electrochemical driving force for calcium to enter cells. Right? This is part of why its equilibrium potential is so high. So we can see that calcium ions would not have equal and opposing forces until we get to 137 millivolts. So that's even higher than sodium, right? Where we're starting out at our resting membrane potential. The direction of these arrows is the same as sodium. Everything's pointing in. As we get positive, we would eventually flip that EDF. That's get very, very, very positive in order to stop the movement of calcium into cells. When we get there, all you'll need to know is that calcium goes into cells, and that's going to be part of how we release neurotransmitters. But I want to make sure that we do know that calcium goes into us. Okay, questions about calcium here? And I noticed at the end of last time, nobody had put in a question when I pulled it open on my phone, but some of you got in there as we were continuing to talk. So I just wanted to touch base on those questions. So last time we were talking about graded potentials and action potentials when we left off. So our graded potentials are little small charges that are accumulating, and our action potentials are eventually going to be really big, large charges that we see running down the axon. Okay. But we had two questions here, okay? So we said that the graded potentials are partially different because we can have strong ones and weak ones versus an action potential is all the same. So actually an action potential really is always the same. So it's always going to positive 30. So while we will have negative stimuli, the negative stimuli are not going to be. What's that? Anybody know? It's so much fun. All right, we'll move on. So long as it's not a fire alarm, is really what my question is. Okay. Somebody let me know if we all need to evacuate. All right. So, action potentials will really always spike to positive 30. We're going to hopefully talk about them today, so they'll never be inverse. But we will have negative stimuli that move the membrane potential down. But those would be graded potentials, and they're going to stop us from firing off an action potential. So the second question, when we're looking at different sort of local charges throughout the cell, yeah, we can think of the number that we're using as an average of these. We're not going to have to calculate anything exactly, but yeah, that total number when we look at the cell would just be referring to all of the kind of distribution of ions in the cell after everything is kind of mixed together. Okay, so I wanted to make sure that those of you who asked questions, I wasn't ignoring you. I just got to them late, saw them after we done. Okay. So for our graded potentials, we're adding together stimuli to figure out whether we're going to fire off an action potential or not. So whether we're going to communicate with another neuron or potentially a muscle cell at all. We're doing this based on the signals, the stimuli we get coming in that cause changes, local changes to our membrane. So in order to create an action potential, to elicit an action potential, to send off an action potential, we're going to have to reach thresholds. So the threshold that we're trying to get to is negative 55 millivolts. Unless we get to negative 55 millivolts, no action potential, no matter what happens, essentially. Okay. So we can refer to graded potentials and other potentials in general as either excitatory or inhibitory, which are going to pair up with our ideas of depolarization and hyperpolarization. So an excitatory potential is depolarizing, an inhibitory potential is hyperpolarizing, and we'll talk extensively about those terms depolarization and hyperpolarization as we move through the rest of our unit. But looking at these right now, these are referring to directions, okay? So when we talk about polarity and the cell having polarity, That has to do with that negative or positive on the membrane potential. And so when we say that something is depolarizing from that resting membrane potential of -70, we depolarize. We're going to start out by getting closer to 0, right? So essentially we're starting out by like getting rid of that negative. So depolarizing is going to be when we see our membrane potential go up. The depolarization you see is here. So we got a graph of our membrane potential in millivolts. We wanted to depolarize it. We go up. This would also be excitatory, right? Because what we're trying to do is get to -55 millivolts to fire off action potential. Okay. So when we say excitatory, right, we're thinking about getting it excited, trying to send something off, getting it more likely to fire an action potential. So if we stack up enough depolarizations, right, eventually we will hit that -55, at which point we'll see the action potential fire off. Okay, so that's why those two terms are linked together. And so which one we use is going to be basically emphasizing one or the other of those ideas. So if we say depolarization, we're probably focusing on that membrane potential, thinking about ions, thinking about those charges. If we describe something as excitatory, the same thing is going to be happening, but what we're interested in is like, okay, is this making a muscle fire? Is this neurotransmitter getting released? And it's just like a different in focus, not a difference in the total situation. So this is the way I would think about it. Inhibitory is in the other direction, okay, but the same kind of idea. All right, so our threshold up at -55. So to inhibit something, right, like to not have a reaction to something, right? For a neuron, that means to be less likely to fire off an action potential and to talk to the next neuron in our chain or our muscle cell. So to inhibit the action potential, it means our membrane potential is getting farther away from that threshold. If we get farther away from threshold, we'd be inhibiting an action potential. It was now going to be harder for us to send off a signal, right? And if we're thinking about the direction of that change for the membrane potential, we're thinking about the charges, we're thinking about the ions. We've described that dip as hyperpolarizing. Okay. Depolarizing, we're getting closer to 0, kind of washing out that negative. Hyperpolarizing, we're getting more and more negative, right? We go down to like -90, right? We're even more polar, even more negative than we were before. So as we talk about our action potentials, we'll mostly be using the terms depolarization and hyperpolarization because these are going to be phases of the action potential. But when we then move forward and talk about synapses and neurons talking to each other, we're going to see this excitatory and inhibitory terminology. But it's helpful to realize right at the get-go that these two things are really linked together. So if we think about our ions, we got a positive ion. We want to think about these concepts. So if we want a positive ion to cause a depolarization and excitatory potential, those two concepts can be linked, just different in emphasis. That positive ion going to move into our cell or out of our cell? Written into the question, but also think about what ion do we think might be the one doing this now that we know which direction our ions want to go. Take another couple seconds if you want to put in an answer. Okay, good. So we're mostly on the same page. Perfect. So what we're thinking about is our cell, right? So we got a cell. It's starting at the resting membrane potential of -70 millivolts. And to cause a depolarization or excite this neuron means we're trying to get closer to that threshold of -55. We're going to go to 0. We're depolarizing. So we have to make this more positive. Okay, so to do that, a positive ion is going to have to move into our cell. So cause depolarization and help positive ions moving into this. Anybody want to hazard a guess at which ion we're probably thinking about here? Sodium. Yeah, that's what I talk about all the time. Okay, so sodium is our ion that wants to move into the cells of the two that we've been talking about a lot recently. So sodium ions moving into the cell is what is going to be causing our depolarization in our neurons. So I had these question slides up part way through last time, and I said we'd go over them briefly. So this is directly linked to that question just now, right? So if we have a depolarization, part of how this is going to happen, right, is that we have a cell. It has channels on it, all right? We can open and close these channels. One of the ways we can have them open and close is by binding on neurotransmitters, our signaling molecules, right? So this is kind of like how enzymes worked, right? When you have something bind onto a protein, the protein changes shape. So this little blue triangle is a neurotransmitter. It might bind onto this channel and open it and allow sodium to move in, right? The sodium moving in would cause that membrane potential, that -70, to start to creep up towards that threshold of -55. So that's our depolarization. We can also think about the reverse here. Same deal, we're going to have a cell. We're going to have a channel that was closed, but gets opened when we have some sort of neurotransmitter bind onto it. So probably a different neurotransmitter, but we're still going to draw it as a blue triangle. But this time we're interested in potassium. Okay. So take a second, think about what direction potassium moves here. Hopefully, we all remember that potassium wants to move out of the cell when we're at the resting membrane potential of -70. So this is how we could end up with hyperpolarization. So this charge getting more and more negative, right? So -70, -80, -90, until we get to potassium's equilibrium potential of -94. So this is how we would cause inhibition. This is how we would cause hyperpolarization. So back to our graded potentials. So our graded potentials are going to be little changes to our membrane potential, and we're going to try and add them up to get to -55 if we want to fire off an action potential. So in order to think about how we can add them up, we have to know that graded potentials can sum. So all that means is like you can take one graded potential and tack it on to another graded potential and eventually get up to -55 by having either repeated stimuli in time, right? So this is like another neuron going like, hey, 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 do something. That would be temporal summation. So adding up those graded potentials over time. Or we can have spatial summation. So spatial stimuli are going to be different stimuli happening at the same time, right? So instead of having one neuron poking the second one over and over, think about it like you have 3 of your friends, 5 of your friends, all telling you to do the same thing, right? Like you're adding up that signal. So we have that neuron being poked from like 3 different places at once. So this is different stimuli that add together. You can have either of these versions lead us to an action potential or not. Now for our graded potentials can be depolarizing or hyperpolarizing, excitatory or inhibitory, positive or negative, unlike our action potentials, which are always the same. Okay. So when we're adding them up, we would need to know what we are adding together. So here we have a positive graded potential, positive depolarizing graded potential, another positive depolarizing graded potential, but gets us all the way to -55. Shoot off our action potential. Here we added together graded potentials as well, but we had a positive graded potential, so a depolarization added with a negative graded potential, a hyperpolarization. So when both of those things happen at once, we don't end up firing off an action potential because they can go out. So we're gonna just do a quick little drawing of how each of those are happening. So we're starting with temporal summation. So this is the one that happens in time, right? So if we think about our cell, 9.1, 9.2, 9.3. We're gonna start all of them. We're just assuming we're starting at -70. So what we're thinking about, we're opening some type of channel, probably a sodium channel. If we're depolarizing, a potassium channel. If we're hyperpolarizing, so I'm just going to show that signal coming in, our stimulus, into the cell. So at this point, instead of being at -70 at that point, maybe we get to -60 here. Okay. And we know that that would sort of spread out a little bit because we have decay of our graded potentials. So this patch of membrane is at -60. This one might be at -65 and so on and so forth. This is really where we're focusing on the graded potential adding up is at the axon hillock. That's just a feature of graded potentials. So I'm not writing it on here because it's not specifically a definition of temporal summation. A temporal summation is that if we move that membrane potential to -60, take away the stimulus, right? It's going to take some time for us to restabilize at that resting membrane potential. So at time point 2, even without the stimulus, maybe instead of being at -60, it's slowly washing out, but now we're at not all the way back to -70, maybe we're at -65. Okay. And then at time point 3, we have that same stimulus come in again, right? That original graded potential, that original depolarization hasn't totally washed away yet. At time point 1, it took us from -70 to -60. So now at time point 3, take us from -65, same strength of the potential, right? But now it's going to get us to -55. So it's a threshold, in which case now we would fire off an action potential. So that's our temporal summation, temporal time. Just adding these up over time, and that's how that would happen. For our spatial summation, this is all happening at one time point. Okay. So this is a little trickier, but we're still just trying to get to threshold, right? And all that's happening is that we're thinking of two signals coming in at once. So here's signal 1, signal 2. They're coming in different spots, not in the same spot, because they couldn't come in the same spot because it's already occupied. Okay. So the two coming in at once, right? They're going to have a big effect where they originate. That effect is going to get smaller as we move away from that point. And we're thinking about it going towards the axon hillock, which is why I've drawn it in that direction. All right, they're both doing that. Okay. But we can see that our patch of membrane that we're interested in is going to be affected by both of these, right? So not by the full amount that's happening at the point where it enters, but both of these changes to our membrane potential are going to add together at this point. So if we add them together, if we get to -55, it's the threshold here at this point, we would also fire off an action potential. Right. So let's do a Q&A session. So I think if you have questions at this point, let's address those. There's some lag time. I will keep checking in a couple of minutes, but I'm not seeing anything in right this second. Oh, perfect. Okay, so the point where the signals are meeting, okay, when we're thinking about our neuron, and I think that yellow probably wasn't showing up super well, so I'm going to do orange. Right, our neuron is going to have dendrites and a soma. Okay. And then we have the axon hillock leading us into the axon, which is this tube, and then our axon terminals. Okay. Spaghetti fingers here. So the point at which we're interested in that summation happening is going to be right here in the axon hillock. So axon hillock. It's in terms of math, we could add it together somewhere else, but we don't care about it adding together somewhere else because the axon hillock is where we fire off or don't fire off our action potential. So, talk about membrane potential changes based on their direction. So we've talked about depolarization and hyperpolarization. So our reference point is that membrane potential, or sorry, the resting membrane potential of -70. Okay. Depolarization brings us up from -70. Hyperpolarization brings us down from -70. As we move into the action potential, we're going to see two additional terms here. Okay. So we're also going to see repolarization So repolarization, think returning to that resting potential. So repolarizing, getting back to -70. It's going to happen after a depolarization has pushed us up. When we pull back down, that's our repolarization. So that's our additional term here for our directions. Okay. So one more question. So we want to make sure that we can predict these. So we've talked about directions of the ions, we talked about depolarization, and we're going to be thinking about repolarization. We now know it's going back down after a depolarization. So what we want to know is what ion is going to start us off in the depolarization phase of our action potential. Then as our action potential hits a peak, we're going to see that peak going back down to -70. We want to know primarily what ion is responsible for that. A few seconds. I'm breaking down this question. We're looking for first depolarization phase of our action potential. And then second, we're going to think about the repolarization phase. Let's take a look at how it did. Okay, great. So most of us are here, right? So depolarization in our action potential is going to start by having graded potentials add together, get us to -55. So starting to depolarize to excite that neuron to -55. Then we're going to see that that action potential shoots up all the way to +30 in our depolarization phase. So that's all the responsibility of sodium pulling us up towards its equilibrium potential of +60. Sodium wants to come into the cell, and during that depolarization phase, we're going to let it. To bring us back down, to repolarize, because we want to go back to rest, we're going to need to find an ion, positive ion, to flow out of our cell. So our equilibrium for potassium is at -94, right? So when we open our potassium channels, we are going to go back down towards 0, then past 0, repolarizing our neuron as potassium leaves the cell. Okay. So we are going to move into our action potential now. I just want to make sure that we remember what channels we've talked about so far. Okay. So when we were talking about why we are at the resting membrane potential of -70, right? This is due to leak channels that are present throughout our neurons, so throughout the whole cell, right? And they're always open. We have a sodium potassium pump that's keeping our concentration gradients from washing out. So those concentrations plus these open channels and our electrical forces lead us to be stable and at rest at -70 millivolts. Okay. I drew some on today, so we can now add on that ligand gated channels. So a ligand or ligand is something that binds on to something else. Okay, so binds onto a protein. In this case, binds onto a channel. Okay, so this is going to come in mostly when we're talking about neurons talking to each other. and when we're thinking about neurotransmitters. But this is what we had happening to cause these graded potentials. So our stimuli really were things that come in, open a channel and allow ions to move, right? So these ligand-gated channels are going to be on the dendrites, which are collecting those incoming stimuli, and on the soma, the cell body of that neuron. We are moving in right now to our voltage-gated channels. Okay? Our voltage-gated channels are why we care about that threshold. Okay? So the threshold of negative 55 millivolts is important because when we get to that charge, we have these voltage-gated channels change shape and start to open up. Okay? So these voltage-gated channels basically respond to electricity. So they're responding to changes in that membrane potential. We're going to be thinking in our neurons specifically about sodium and potassium channels. So we're going to have sodium voltage-gated channels. We're going to have potassium voltage-gated channels. And this is what's going to control the phases of our action potential. So we're going to see them in the axon, where we send our action potential down the line. We're also going to see them really, really concentrated at that axon hillock. So that was that place where we were just looking, that we're looking at those graded potentials summing together, especially those spatial summation ones, right? That's right at the beginning of our axon. So we care about voltage-gated channels there in specific, because that's the region that if we fire off an action potential, it's going to happen there. So we have a high concentration of voltage-gated channels right there. When we get to synapses and talk about the release of neurotransmitters, we're going to think about calcium channels. Those are all the way on the end of the neuron at our axon terminal. Okay. Voltage-gated sodium channels. Of our two types of voltage-gated channel, the sodium ones are the more complicated ones. Okay? They're more complicated because they have two gates within them. Okay? So we're going to notice right off the bat here that when we're looking at the sodium channel, right, it has this wall forming this pore. We got a door in the center, right? So when we say we have a gated channel, this is the kind of situation we're thinking about, right? So we have a door here that can either be closed or open, right? And the sodium channel actually has a second door down here, right? So this door can also swing closed. Right? So this is how that one would close. So when we're thinking about sodium voltage-gated channels, we have to think about both of these doors, because in order for a sodium ion to actually get through, we have to have openings in both places, right? A sodium has to be able to get to that first door, that first gate, and pass. And then it also has to be able to continue all the way into the cell. So it has to pass through that second gate as well. So if either of these is closed, you're not going to have any sodium flowing into your cell. Okay. So for our voltage-gated sodium channels, what they are responding to initially is that change to threshold. So if we have graded potentials that sum together and get us negative 55 millivolts, we have a change, conformational change, a shape change in that sodium channel. Okay. So what we see happening, we have the same picture, even bigger. Okay. So at rest, so at our resting membrane potential of negative 70, the situation that we have is that our activation gate, so this first gate that sodium would have to go through, is closed. Right? So sodium doesn't get in because if it tries, just immediately bounces back off that activation gate. Right? At this point, the inactivation gate is actually open, but it doesn't matter because that's the one on the inside of the cell. So the sodium can't even get there. So it doesn't even know it's open. When we hit negative 55 millivolts, when we have that initial depolarization to threshold, okay, what we have happen is that activation gate opens, right? So at -55, these voltage gated sodium channels start to open. And now sodium can move through, right? So the activation gate was open, was closed, now it's open. Sodium moves through the first gate. The inactivation gate was already open. Still in that state here for our depolarization. Sodium gets all the way into the cell. That cell gets more positive, it depolarizes. There's also a timing bit though in these voltage gated channels, right? So the timing bit comes into play with that inactivation gate. So we don't want sodium to flow through forever and ever and ever and ever, okay? So we are going to close that sodium channel back. Okay? So what happens first here is that after a millisecond, that inactivation gate that has been open until now swings through and closes up that inside part of our sodium channel, right? So sodium could still go through the activation gate, which is open, but it can't travel all the way in because it gets stuck here on the inactivation gate. Finally, to go back to rest, that inactivation gate loosens up, opens up, goes back to its original state, as does the activation gate. So the activation gate goes back to being closed. We'll see the effects that this has on the neuron overall as we think through our action potential. So these two gates are associated with the channel. They're voltage dependent, so they respond to changes in the membrane potential. Both of them are voltage dependent. The activation gate is just dependent on that voltage. It's not about the time here, really. It opens at the threshold and at depolarization, right? So it's allowing sodium to move in. This is basically going to create one of our examples of where we see positive feedback in the body, because if you think about it, okay, so as we see sodium flow in here, now we have positive charges. If you have another voltage gated sodium channel right next to it, right, if this portion of the membrane wasn't at -55 yet, as those charges spread out, right, move to the side, it's going to trigger this next one in the line. So this is going to happen like dominoes and allow these charges to flow down the cell. So when we talk about how our action potential gets propagated down the axon, that's basically what's going to happen. If we're thinking about the inactivation gate, it is responding to voltage, but it's also responding to time. So it's just kind of slow, right? So it responds to voltage, but it takes it a second to realize, okay, I need to close. Okay, so its response is to close, but it takes a millisecond for that to happen. Okay, so it both opens and closes during the depolarization phase of the action potential. All right, and another question here about stimuli. Okay, and if you have more questions, pop them up now. Hopefully they will appear as you type. So when we're thinking about stimuli and affecting the membrane potential, no, we are focusing on the positives because we're leading ourselves to an action potential, because that's like our next topic is understanding how they fire off and why. But stimuli can also make that membrane potential more negative. So that's the hyperpolarization piece. So if instead of opening one of those channels for sodium, making that membrane potential positive, getting us closer to threshold, depolarizing and excitatory. Instead, we open a potassium channel, make the cell even more negative, hyperpolarize it, inhibit, then we're moving farther away from the threshold. Okay. So for our voltage-gated potassium channels, I like them better because they have only one gate that we have to worry about. All right. So for our voltage-gated potassium channels, what we have happening is that around positive 30 millivolts. So this is a different number we're interested in. So positive 30. So this is not threshold. This is actually going to be the peak of our action potential. At positive 30 millivolts, that voltage gated potassium channel opens. So potassium is going to start leaving the cell when we get to positive 30. Okay? So this is what's going to eventually pull our membrane potential back down, repolarize us to the resting membrane potential as potassium rushes towards its equilibrium potential of negative 94 millivolts following that electrochemical gradient. So if we wanted to sum up the states of those potassium voltage gated channels, they only have one gate, all right? So we don't have to worry about activation, inactivation gate. Depends on voltage. This does also depend on time. We have a little bit of a time lag here. This is essentially negative feedback on our action potential. Our membrane potential rises to positive 30 during our action potential. Potassium channels opening are what drag it back down to rest. Okay, so negative feedback, a change in the opposite direction. I'll actually do this one next time. I want to show you this graph and then we will go. Okay. So what I want you to realize about those voltage gated channels is that what we're doing is we're affecting the permeability of the membrane to those different ions. So what we're causing really with those voltage gated channels opening and closing is we're changing how permeable the cell is to sodium, and we're changing how permeable the cell is to potassium. So that P is for permeability here. So we could graph the permeability to sodium and potassium versus this red line, which is a red line showing changes to the membrane potential. Specifically, it's showing you what an action potential is. So we'll pick up here next.